Hey everyone, this is Mr. Sal, and today we're going to be looking at simulations for probability events and activities, whatever you want to call them. And also we'll look at some other ways to use tree models to identify outcomes and results for specific events or activities, whatever. Alright, so we're going to start this off by looking at what we call simulations. So a simulation is an experiment that models the real life or a real life situation. So for example, so we would be looking at maybe perhaps rolling a dice. Alright. So we have the possibility of getting even or odd, for example. And it would be helpful to know the probabilities of these. Okay, we're not actually doing it. So we're looking at theoretical probabilities. What is the theoretical probability of even? Rolling an even from dice? Yeah, 1/2, right? 3 out of the 6 faces are evens, so yeah, we could say 1/2. What about odds?
Same.
It's the same. 3 out of 6, which is the same as 1/2, right? Yeah. So a simulation would be a different thing to do, a different experiment, a different activity that would give us the same odds, but it would not actually be rolling of the dice. So one of the suggestions that we could look at is maybe tossing a coin. Why does this work? Because if you get heads, which maybe we say is the same or would represent the evens, then you have a 1/2 probability of getting the heads. Again, which would represent evens. And then odds would represent tails, which also is that probability of 1/2. There is one more that we could look at though. Or it's possible we could go in and make a spinner, like this one right here. And what would we do to the spinner to make it represent evens or odds? Bam, let's just split it right in half like these. We'll assume that's a straight line. And now if you put the spinner on that dot and then just spin it, then maybe we say the left side there is evens, maybe. And then the right side can be odds. So a spinner like this would be another simulation of rolling a dice and getting evens or odds. What if I said we're going to toss a coin 6 times, and that would be a good simulation? Would that be a good simulation right there? See, now that changes everything. Tossing a coin once would work, but not tossing it 6 times would work, because you get lots of different outcomes, like heads, 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 tails, tails, heads, or tails, 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 tails. Okay? Which gives you a lot more different possible outcomes once you start tossing the coin many times. We're going to see problems like that on the test. So let's look at another example, and then we want to find a way to simulate this. Let's say that a store is handing out some good old coupons, right? And one of the coupons is 10% off. All right, so this is at some kind of grocery store. We'll say we got 25% off, 50% off, 75% off, and 90% off. Okay, so this is at some kind of grocery store. Maybe it's off an item or off of your total purchase. Doesn't matter. But they're giving these coupons away as people walk in the doors. They're just pulling one from a stack and then handing it to a customer. So it's random. And it's equally likely that you'll get one of these as it is the others. Okay? So what we want to do is create some kind of simulation that would allow us to simulate the probability you get any one of these, but it has to have the same probability. So we're going to simulate this. The question is how? How will we simulate it? All right, that's excellent. 5-sided spinners. Actually, spinners are pretty easy way to know that you can just split it up, right? And then you will have equal chances on a tease? All right, something like a tease. So again, we put the spinner right here at the point in the middle. We spin it. And then just to simulate this, we could say one of these spaces represents each one of these different types of cowpons. So this spinner now represents the probability of getting these cowpons equally. And so, in other words, if we didn't want to hand out cowpons, we could have used a spinner and said, hey, you get 10% off now. Yay. All right, there is another way, though. One way to do it is to perhaps... All right, another way to do it is to maybe make a bag, like these. And then what you would do is inside, you could put in some kind of marble or tile thing. And this one represents some number. This one, how many do we need, though? 5. And they should be maybe different colors. Or they just say directly on there what they represent right here. There we go. Now they should be the same size, but that's pretty close. Suppose the ratio of left-handed peoples to right-handed peoples is 1 to 10. Create a simulation for the number of trials it takes to get a left-handed person. So what kind of simulation can we do right here? Bam, a spinner is always a good one. That's good. This is a good question. How many spaces does the spinner have to have, though? 11, right? You got 1 left-handed person and then 10 right-handed peoples by this ratio, right? Left 2 right-handed people, so we do need 11. So a spinner with the 11 equal spaces would work as long as one of the spaces represents the lefties up and down. But we could do another one. I like the bag example as well. And what would we put in the bag? All right, we got 11 pieces, maybe tiles, marbles, blocks, doesn't matter. But how do we make them different? All right, you could do that. You could put 11, I don't know, we'll do tiles again. 11 of these, and one of them has to have lefty on it, right? And the others wouldn't have rights on them, or R. So another way perhaps you could do it is just to make the lefty a different color. Right, account. And then you have someone pull out a tile randomly from the back, and that would represent choosing a left-handed person with this ratio of 1 to 10, left-handed people to right-handed people. Frequency of an experiment based on large number of trials. So I think what this is trying to tell us is that the more trials you do, the closer you should get experimentally to the theoretical probability. So we're looking at win the spin. We want to find the probability that player 1 wins the spin. So what's going to happen is you got player 1 who's going to spin spinner A, and you got player 2 who's going to spin spinner B. Now these have different numbers on them, but we've got to determine what the probability of each player 1 and player 2 to win. Now to do this, it will be helpful to create a probability model for us for win the spin, and that will determine what the outcomes are so that we can determine who is the most likeliness to win. Okay? So let's start our question off right now. How many outcomes do we expect? Looking at these. So, correct. So looking at these, it's kind of like the compound probability stuff. Spinner A has 3 outcomes. Spinner B has 3 outcomes. So the total outcomes is 3 times 3, which is 9, which should be represented very accurately in the table. All right, so let us make our tree diagram. All right, so let's identify what's happening right here. We got person 1 spinning A, and then the second thing that happens is player 2 will spin B, and this should produce the results that we need with the outcomes. All right, so just looking at spinner A to start, what are the possible outcomes for spinner A? for person 1, right? Yeah, you can get a 1, a 5er, and a 9er. Now let's say that person 1 spun a 1 from spinner A. Then from that 1, perhaps person 2 could spin a 3, maybe a 4, but maybe also an 8. Now again, this produces some of our outcomes right here. That's a 1 and a 3, a 1 and a 4, and then a 1 and an 8 right here. Well, on both of these, if person 1 spun a 1 and then person 2 spun a 3, who won?
Person 2.
Yeah, person 2, right? So person number 2. What if they spun a 1 and then a 4? Then who won?
2.
Still person 2. What about a 1 and then an 8?
2.
2. All right, so those are the outcomes and the results, but we need to do the same thing now for 5 and 8. All right, so there we go. And these correspond to these right here. So we'll have 1, 2, 3, 4, 5, 6 more. And now we got a 5 and a 3. Who wins in a 5 and a 3?
1.
The 5 does, so person 1 would win right there. All right, let's list these other ones. So there we go. There's the outcomes, all of them. Now let's determine the results, though. If they spun a 5 and then a 4,
1.
that would be person 1. 5 and 8,
2.
2. 9 and 3,
1.
9 and 4,
1.
9 and 8,
1.
1. All right, so how many outcomes do we have? 1, 2, 3, 4, 9. 9, all of them right here, which was what we expected. But now we should find the possibility that person 1 wins. And what is that probability for us? Yeah, there's 5 possible outcomes where person 1 wins out of 9 possible outcomes. Yep, you can count them. Person 2 will win 4 of the outcomes out of 9 outcomes. Let me ask you this as well, just relating it to a previous lesson that we had. Does this represent a fair game?
No.
Why not?
This question is more likely to win.
Correct. Yep, one of these spinners is more likely to win than the others. So looking at number 2, how many possible outcomes are there? 9. How do you know? Well, we did right here. That's what we call the fundamental counting principle. You take the number of possible outcomes from one experiment and multiply it by the outcomes from the next one, and then you keep moving on if there's more. All right, number 6 right there, we've answered those other parts. What's the probability of a tie in this? What's the chances that they tie? How many results show a tie? 0 of them do out of?
Yeah. Out of 9.
9. So there's a 0% chance that they will ever tie. All right, we're going to demonstrate an example of these. And to do it, we will need the math ball. Okay, so we'll get 10 shots out of this. And then we're going to find, because this is an experiment, that'll be an experimental probability. Then we'll look at the situation that is at hand, okay? So go ahead and take the 10 shots. We're going to look at shots made and shots missed. Here, we got 10 shots. Let's just imagine that it was over a season, so there's lots of shots on that, okay? And this isn't basketball. Well, we can relate it to basketball. But let's first look at the probability of a shot made and a shot missed. So you guys tell me, what's the probability of making a shot by the count?
7 out of 10.
Yeah, 7 out of 10, which is also 70%. We'll identify that. What's the probability of a miss?
3 out of 10.
Yeah, 3 out of 10, which is also
30%.
30%. So we have these two probabilities, and thank goodness we took 10 shots right account. And that shows us now some pretty nice probabilities to work with, okay? So here's a scenario. I guess I'll type it. So Kenny is in a one-on-one situation. We got 2 shots, kind of. For sure, Kenny gets the 1 shot. If Kenny misses the first shot, no second shot. If Kenny makes the first shot, another shot. Okay?
Fails.
So what we need to do now is find the probability of winning. All right. Now it may be helpful to make a tree model on these, but it'll be very similar to the one we just did with the two spinners. We got to find the outcomes and then determine the results from each of the outcomes. All right. Don't forget, we're basing Kenny's numbers off of these experimental percentages.
You hit the whiteboard lower.
So I'll get this one started for ye, and then hopefully you guys can finish, all right? To start out, we got the first free throw, and then after the first free throw, possibly could be a second free throw. Now from these, we should be able to find the outcomes, which will also determine the result. So this is a good way to start your tree model. Look at the two things in this case that are happening, or all the things. Look at your outcomes and then determine the results from right account. So it is important for us to get the tree diagram first, which will tell us the outcome and the result, and then we can find the probabilities of each. All right, let's look at the first shot. And so for the first shot, it is possible for Kenny to either make the shot or they could miss the shot right here. Now remember, if Kenny misses the first shot, there is no second shot. But if Kenny makes that first one, then it is possible that Kenny could either make or miss the second one. So looking at the outcomes, all right, so Kenny can make the first one, make the second one, make the first one, miss the second one, or if Kenny misses, probably game over right here. So we need to remember, not that I wrote it, but it's part of the problem, that Kenny's team is down by 1. It should help us to determine the results. If Kenny makes the first one and the second one, what is the result?
A win.
A win. If Kenny makes the first one but misses the second one, what is the result? Tie. And if Kenny misses the first one, lose. So the question is now, which of these, what is the which of these has the highest probability of taking place? Is it the highest probability that they will lose, tie, or win? 70% free throw shooter. Let's figure out the exact probabilities with that in mind, all right? So right now, we would kind of assume that they should win, but it may not come out that way completely. Let's find out. All right, so let's identify these. Kenny has a 70% chance of making and a 30% chance to miss. So, using the compound probability stuff, we'll go into these. Let's look at the winning scenario, so we'll separate these. So what's the probability that Kenny will make that first shot? 70%, which is a decimal, is 0.7. And then what's the probability that Kenny will make the second one? Still 70%. So to find this actual probability, the probability of winning would be 0.7 times 0.7, which is 0.49, or that'd be 49%, which is pretty high. When we look at the probability that Kenny will make the first one, which is 70%, and then miss the second one, which is 30%. So the probability of tying would be 0.7 times 0.3, which is 0.21, or 21%. The probability of losing right here, let's find a good appropriate color like the gray. Well, the probability of missing is 0.3, which is 30%. Now, when we look at these, We got win, tie, or lose. If we add all these percentages up, what do we get? 49 plus 21 plus 30 is 100%. So there's a 100% chance that Kenny will win, tie, or lose the game.
Is it 30?
Now let me ask you guys these. Is it more likely that Kenny will lose the game or not lose the game?
Not lose.
What's the probability then that Kenny will not lose the game?
70%.
Yeah, right. We got the 49% for win, 21% for tie when we combine those. This is 70%, which is also the same as the make from the beginning, right? The 70% back here. All right. All right, we're going to say that there's 4 seats, right here. And, I don't know, we'll say that you got 6 pals. Well, you and 6 pals. No, you and 5 pals, so 6 people. So we want to figure out how many different ways we can arrange these 6 people in these 4 seats, right here. Okay? This will be, it'll be like this on the test as well. Okay. Now, usually we should have 6 seats, right? So 2 people are going to have to go home. We'll just kick them out when we finish, okay? But we're looking at these. We'll number these so we can keep track of them a little bit better. So we're going to sit someone down in seat number 1 first, then 2, then 3, and then 4. So, number 1, seat number 1. How many different people could we put into seat number 1?
4.
6. So the next question is, how many people could we sit in the seat number 2? 5. Because one person now is seated in seat number 1. So now you've only got 5 choices in seat number 2. Now you've set a person in seat 1 and 2. And for seat 3, you've only got 4 peoples to work with. So in seat number 4, you've got 3 peoples to work with.
Times them all.
Then we're just going to multiply all of these. This means, so multiplying these, we get 360, right? So that means there's 360 ways to sit these 6 people in these 4 seats.